Section 11.4 is on conditional probability. The probability that an event will occur, given that another event has already occurred, is called conditional probability. This exists only when the two events are dependent. And we write it like this: P, and then in parentheses B/A, and it's read the probability of B given A. Here's an example. Let me scroll down a little bit here. So the table shows students by gender and by type of school in the year 2005. You choose a student at random. What is the probability that the student is attending a four-year college given that the student is male? So first thing we need to do is find out how many total males they are. So we're going to total up this column, and I'm going to get the total of males. Is 7,539. Okay. Then, given that they are male, so we're only focusing on that column, how many of them attended a four-year college? And that's 4,324. So 4,324 out of the 7,539 males gives me approximately a 57.4% probability. Here's another example. Americans recycle increasing amounts through municipal waste collection. The table shows the collection data for the year 2007. What is the probability that a sample of recycled waste is plastic? So, what is the probability that given it is recycled, it's plastic? So we're going to total up this is in millions of tons, the total millions of tons just for recycled. So doing that, we get 79.4 million tons, and then out of that recycled, 2.1 million tons were plastic. So we do that division, and we get that that's approximately 2.6%. So the probability that a sample of recycled waste is plastic is 2.6%. Conditional probability can also be calculated using the following formula. The probability of B given A is equal to the probability of both B and A occurring divided by the probability of just A occurring. Let's use that formula in an example and see how that works. Researchers asked shampoo users whether they apply shampoo directly to the head or indirectly by using their hand. Use the formula above to find the probability that a respondent applies shampoo directly to the head, given that the respondent is female. So the first thing we want to do is find out what is the probability that the respondent is female and applies it directly to her head. So there are a total of 50 respondents. If we total up all of these numbers, so male and female directly to the head and into the hand first, that's a total of 50. And out of those, 6 females apply it directly to their head. So that's 6 out of 50. And that's going to be my P of A and B. Okay, then what is the probability that a respondent chosen at random is female? There's a total of 30 females, adding 6 and 24 out of a total of 50 respondents. So then the probability that the shampoo is applied directly to the head, given that the respondent is female, is 6 over 50 divided by 30 over 50. You can plug that into your calculator or write it out as division of fractions. That's 1/5, which is equal to 0.2 or 20%. So taking the formula above, let's take a look at that formula up above here, and if I multiplied both sides of that equation by the probability of A, so in other words cancel this out and move it to the other side, I get this formula here. I can say that the probability of A and B occurring is equal to the probability of A occurring times the probability of B occurring given that A exists. And we can use that to find the probability of dependent events. Let's use a tree diagram to do an example of this. So the chance of rain for tomorrow is 60%. If it rains, the chance of lightning is 80%. If it does not rain, the chance of lightning is 5%. So we're going to draw a tree diagram to find the probability that it will not rain and there will be no lightning. Okay, so for the tree diagram, I'm going to start like this, and I'm going to label one of these with an R for rain. I'm going to make this one a little longer and label this one with the probability, or the title, an R for no rain, because it's either going to rain or it's not going to rain. So the probability, it says the chance of rain for tomorrow is 60%. I'm going to go ahead and write that as a decimal. So if the chance of rain tomorrow is 60%, then the chance that it's not going to rain is going to be 40%. And I'll write that as a decimal also. Okay, then it says if it does not rain, the chance of lightning is 5. So off of the does not rain branch here, I'm going to do lightning, and I'm going to do no lightning. So what did it say? The chance of lightning is 5%. So as a decimal, that's 0.05. Subtract that from 100, so the chance of no lightning is 95%, or 0.95. And oh, I forgot the second one there. Okay, I jumped ahead to the does not rain. I forgot this one. If it does rain, then the chance of lightning, if it does rain, the chance of lightning is 80%. So the chance of lightning, no lightning, is going to be 20%. Okay, so again, we have rain, no rain, and off of each one of those we have lightning and no lightning. Now we need the probability of no rain and no lightning. I spelled that right? I didn't spell that right. There we go. Okay, so we're going to start with the probability of no rain is 40%, or 0.4. And then off of that, the probability of no lightning is 95%, 0.95. Multiplying that gives me 0.38, or 38% chance that it will not rain and there will be no lightning. So in this section, we took a look at conditional probability and a couple different ways that you can calculate it.